Hi, Assalamualaikum everyone. Okay, in this video we're going to continue another subtopic because previous video I'm not yet finished cover 5.4, so that's why I will try to finish it all in this video. So over here we will cover where is my mouse? Okay, we will cover the pipeline performance. Sorry, my mouse is not detecting. Wait, okay. So pipeline performance. In pipeline performance, as similar to what I did mention in our previous video about the equation that you need to use. So now here it come to your equation. You need to memorize several equation to be used to check the performance under pipeline uh, concept. Okay, here's some simple measures of pipeline performance, and the unit is using SS, which is speed up. This is a simple measurement of pipeline performance and also relative speed up, and the unit you will use using S. Let the execution time to be as T, whether it is non-pipeline or also using pipeline. You can just always change the units over there, which is for T and it is non-pipeline, while TP with a pipeline. And you can see TN, which is the lower case of TN, it is the cycle time. Same goes TP, also a cycle time, but the difference only at whether it is using non-pipeline or pipeline. Okay, this is the equations that you need to remember if you want to calculate the execution time for non-pipeline, which is equal to Tn, the cycle time. If I give you an example, let's say you have abstract introduction,
It's
and
0 hours.
another one is conclusion. If you have abstract introduction and conclusion, your abstract you are doing it 20 minutes, introduction 40 minutes, and conclusion is 10 minutes. So how are you going to define the Tn? Tn will be 20 plus 40 plus 10. Okay, this will be your Tn without the punchline, because you're going to do abstract first. After done, then you're going to continue with your introduction. After done, you're going to do the conclusion. So this is your Tn, the cycle time. If let's say this one is only one paper, one instruction. If you have several, you need to write several paper, let's say 2 paper, 3 paper. So you're going to times how many time that you did for one paper. Then if 3, you just need to multiply it, isn't it? So this is the equation for non-pipeline. While for pipeline, okay, the same scenario, I will use the T cycle time, your TP. What is your TP? What is your K? K is how many um how many stage ni this one. K is stages, N is instruction. So how many stages that you have, and what is the how many instructions? So we have 1 2 3 3 instruction, and K stages. I just assume, let's say in the question is already give 5, and your time you're going to pick the maximum. Let's say over here is 40. N minus 1 for 2. So then you will get your answer. Just memorize this equation. After this, we're going to look into the example. But before we go and proceed to those example, we're going to see the next equation. So what is next equation is the speed up. It also similar unit with your mana. Okay. It's also similar with here, which is under relative speed up. So speed up, how you going to measure? You're going to compare. Compare is divide using a non and also part line. So if let's say you have first, you of course you're going to divide something that much bigger, divide to smallest. So P, which is with pi line, is smallest, and of course you're going to add all the time for your non-part line model. While for part line, of course you're going to do a parallelly, and you will reduce the time. And same goes to here, because this one you take from previous pages, this, and another one at the at below here is at this part line. So if n is too large, and when t from too large from k, so n too large from k, and when your tn, this one is non, isn't it, equal to k times tp, those a maximum speed is s max is k. So this is the instructions. If let's say n is too large, what will happen, and so on. Okay, now we were given with example. This one is part line with the ideal cases. Why you call non-ideal cases? Non-ideal cases. So non-ideal cases, of course, you're going to have different time for each segment. If ideal, then it's going to be similar. Give 4 segment part line whereby each has delay time as follow. Segment 1, 2, 3 and 4. Delay time for interface register is 5 nanosecond. So it's already given you the delay time. Calculate the cycle of non-part line and part line. So you need to refer back to the equation which that I asked you to memorize it. So for non-piping and also with part line. Okay. This is the solution. You can see over here you have several other questions, but let's take a look the solutions. Of course, you can draw like this. You have the input data, you have the output data, and you must have control. You need your CU. And if you still remember, if you look back to previous subtopic, you're going to see that you need to have all the segments separately with the block, you can see. And this one will be register 1, register 2, register 3, register 4. So each of it, you're going to refer it back. Segment 1 is 40 nanosecond. Segment 2 is 25 nanosecond. 45 and 45. You're going to add it all together. And with also your delay time. This is for your TN. What is TN? T, which is time for your non-pipeline. Next, you're going to see there are several other questions. So now over here we did the recap again. Cycle time of non-pipeline and pipeline. Non-pipeline is easy. You just add it all, and don't forget to add your delay. And this is the TN, which is time for non-pipeline. When you have pipeline, which is called as TP, the longest delay for executions. Same goes what I show. Mana? Oh, I delete. So same goes to all of this. For the non, you're going to add it all, include the delay. And for pipeline, you're going to pick the longest. So this one is the longest, which is 45 nanosecond. So you have 45 plus also your delay over here. Then the maximum the TP will be 50 nanosecond. And this one is for one task, one instruction only. But if you have multiple tasks, what you need to do, which is instruction, there are 100 of instruction. First, you need to look into non-pipeline. Of course, you need to check where is the question? Okay, you need to check on the time durations, 40, 25, 45, 45, and you're going to add it. So this is one time. If you have 100 tasks, you're going to multiple it with 100. So that's why you will get this answer. And for pipeline, please be remember that this is your time, which is your TP. You're going to put it into your equation, TP. And this one is nanosecond, so you need to remember the value later on to put it. And you have the K. K is 1, 2, 3, 4. So there 5 of 4. So you're going to put it the 4 because you have 4 instructions plus 100. What is 100? This is the execution time for 100 tasks minus 1. Later on you will get the value of TP. And you will also been asked what is the real speed. So how you going to measure? You're going to do S equal to T non-pipeline with also T with pipeline. Then you're going to get the answer. And how about the maximum speed up? This is the answer is 4 over here, because I guess you need to check the value of k. Go back to the previous equation. So you need to take a look over here. As maximum equal to k, so your k will be 4, because you have 4 process, 4 tasks, not 4 tasks, 4 segment. You have 4 segment altogether, your k will be 4. Mana dia tadi? Okay. So it easy for you to just reapply into the equation. All the information, all the about the time and delay will be given in the equation. So I already finished on the example number wait. Okay, I already done with the example number 12. Now you're going to see it another example, example 13. There are 4 segments as follow: 1, 2, 3, 4. 4 segments all together. The interface delay is 3 nanoseconds. The simplest block diagram of the pipeline, if you were needed to draw, then you need to see, you need to have 4 segments. 1 segment, 2 segment, 3 segment, and then another 4. But all of the segment will have their own register. See, this is segment 1, this is segment 2, segment 3, and segment 4. So it's easy for me. I don't want to read it with the longest name here. So S1, which is segment 1, called as IF, instruction fetch and decode. Operation fetch or OP, instruction execute IE, and also lastly operand store, which is OS. So you have been asked to draw the space-time diagram and calculate. You already look into the timing diagram here. This is example. If let's say you've been asked to draw in your final exam, in your next test also, you know how to draw it. And you need to measure the cycle time for non-pipeline and also pipeline. By doing it manually, you can know. You just need to add it all together because it is non-pipeline. Then you're going to get the answer. While you can see over here, this is the answer. While for the pipeline model, you're going to pick the longest execution. So this is the longest in duration, plus also your interface that been mentioned. This one, the interface of the delay. Then you total up and summarize it, you're going to get 55 nanoseconds. How about another last, which is execution time for 50 tasks. So this one will be directly multiply with your Tn. So you can see over here. Then you get the result. While for pipeline, you can see this is the equation similar to your previous slide. So you have a time. You need to mention about the K value, which is of course is 4, and as execution 3, and then you need to have n minus 1. So you just derive it until you get the answer. For education time, 50 tasks. You have another 2 to solve, which is maximum speed up and also your real speed up. So you reapply it into the equation and try to do all of this. Now, you already know about pipeline. Pipeline is good for you to minimize time, and there are a lot of other advantages. But, of course, if you come out with any kind of proposal, you propose this pipeline good, this pipeline excellent, and so on, but it must have limitation. Everything in our world have their limitation of range. So a pipeline hazard occur when pipeline or some portions of the pipeline must stall because condition do not permit continuous execution. So if there are interruptions, just a pipeline stall is also referred to as a pipeline bubble. You can divide it into 3 categories under your pipeline hazard, which is resource hazard, data hazard, and also control hazard. You have a resource conflict, data dependency, and branch difficulty. So now we're going to look into one by one, from resource hazard, data hazard, and lastly your control hazard. Under resource hazard, it occurs when you have the resource conflict. What is resource conflict? A resource hazard occurs when 2 or more instructions that are already in the pipeline need the same resources. Let's say you have MOV EX 10 and 8 CX with your AX. Let's say I give you only example. By the way, if you can see, maybe this one need to have a similar resources with the move instruction over here, instruction 1, instruction 2, and need the same resources because it's required to have the register AX. You can see over here, it's stored inside your AX. The result is that the instruction must be executed in series rather than parallel for portion of the pipeline. If this problem coming in, then you can use the solution for your resource hazard. What is the solution? So this figure having 5 stages of pipeline and ideal case. So you can see this is the ideal case without no resource hazard. See you at your time 1, time 2, it's okay. But when you have time 3, you face that F0 and F1 is quite similar things. Okay, we read this. We have conflict with two instructions need the same resources, which is your memory. Data read or write can only happen once at the time. Resource hazard. After you have a problem, you're going to have also a conclusion. There is a lot of intelligent peoples in around the world to come out with and solutions. This is all the short form for the fetch instruction, decode instruction, calculate operands, fetch operands, execute instruction, and lastly write store operand. And this one is 5-step pipeline, which is under idle case. This FO and F1 for your resource hazard. It cannot it cannot do it parallelly. F0 and F1. You cannot do it in parallelly. That's why you're going to wait first and you're going to start here. So you need to reorganize your table. Source operand for instruction 1A, I1 is in memory rather than registered. Idle for one cycle are wasted. You can see the solution. It's shifted to another next time, and this existing will be idle. So conflict of resources introduce pipeline delay. A delay in any stage can cause pipeline stall. That is all under resource hazard. Now we're going to move to second hazard, data hazard. So it is the data dependency. So you were given the example here, example of your source code. You have add EAX, EBX. You're going to add these two numbers, and you have next instruction, which is sub. You're going to subtract your ECX with the value of EAX, registered EAX from your previous instruction. So you can see over here, this is the example, and before this you see this is happening like this without any delay, and now you going to do the delay part. But what is going to trigger for the data hazard? The data hazard occur when there is a conflict in the access of an operand location. Two instructions in a program are to be executed in sequence, and both access a particular memory or register operand. So that's why from here, after you finish, you're going to see while you are doing executions of your instructions, then you supposedly can run, but due to their problem, you are going to do a conflict when you try to reach the operand. That's why you will shift and will be continued as normal. Let's take a look what it happened actually. The data instruction does not update register EAX until the end of stage 5. After your stage 5 is finished, then you can update your EAX over here. That's why you need to wait first for the education for second segment. Then you need to do it as a delay. When you have a proposal of certain informations, you can see over here you have the data hazard. Where is it? You also will have the solution. Hardware interlock. An interlock is a circuit that detects instruction with data dependency and insert required delay to resolve conflict. So this is the hardware interlock for your data hazard solution. Operand forwarding allow the result of ALU to be used by another ALU operation in the next instruction cycle. So that is the meaning by operands forwarding. And another term is delay load. Compiler is used to detect the conflict and reorder instructions to delay loading of conflicting data. So what is the solution? You're going to use your NOP instruction. Solution for data hazard using delay load, which is NOP. You're going to put it in between actually. If you have, I give example only, then you're going to see you are shifted one time. If you have TS, okay, okay. Now, example 15. Consider the instruction given where is or are the problem with pipeline implementation. Briefly justify your answer. So you need to find out. You can see all of them are using a register to store and also using as a stack. So this is the normal actual performance. And when you have a problem, you need to find out what is the wrong. So over here it is between these two steps. The data hazard both are about to access the same register of AH. Solution of your data hazard using delay load, you need to use N or P. So you have N, AH, BH, and then you need to stop it first before you proceed to number I2, which is sub AH with the value of 2. And lastly, your CMP AH 0. As we know that there are 3 categories altogether, here we're going to look into the last is control hazard, or it also known as a branch difficulty. Occur when the pipeline makes wrong decision on a branch predictions, which is change the PC value. It brings interruptions into the pipeline that must subsequently be discharged. And lastly, one of the major problem in designing an instructions pipeline is acquiring a steady flow of instruction to be initial state of the pipeline. You can see over here, for the pipeline, they have the desired operation speed up. We must feed it with long string of instruction. However, 15 to 20% of instructions is an assembly level code are conditional branches. Of these, 60 to 70% tag the branch to the target address. Impact of the branch is the pipeline never really operate in full capacity, limiting the performance improvement that is desired for the pipeline. You can try to read all of this information and try to understand it. Now there are another example with the following instruction. It's give you 9 instruction and pipeline operation with 6 stages. 1, 2, 3, 4, 5, 6. 6 stages all together. And the diagram assumes that each instruction goes through all the stages of the pipeline. Is not true. Example, load instruction don't need WO stages. You can see over here another important, which is most memory system will not permit the accesses of PI, FO, WO occur simultaneously. So what you need to see it is as a desired value may be in cage or the FO or WO stage may be null. So you're going to see that this is the effect of conditional branch on institution pipeline operation. See this part. Assume that instruction 3 is a condition branch to instruction 15. So you have too many instruction until also you have 15, instruction number 15. You're going to see that WO is not going to be considered. So until the instruction 3 is executed, there is no way of knowing which instruction will coming next. So you don't know what is going to be in the next. The pipeline simply load the next instruction in sequence. You can see 4, 5, 6 and 7 as in sequence, and also you might proceed. This is the effect of conditional branch of instruction pipeline operations. Until the end of time, which is instruction 7, the instructions in the pipeline that are not useful must be clear. So this one is not useful, then you need to clear it first. Those at time until 8, instruction 15 and instruction 16 will be fit into your pipeline. So you will move it and start it again. No instruction are completed during time unit 9 through 12. This is the performance penalty incurred because we could not anticipate the branch. So you're going to remove it all here. And this is called as your branch penalty. 4 clock cycles are wasted without full executions of instruction. 4, 5, 6, and also 7. So you can have a comparison, your ideal uh, pipeline, and also an alternative pipeline descriptions with conditional branch. So if you see over here, this is continuous, only it will plus with the one durations. While for your with conditions of branch, you need to remove basically unnecessary fields before you proceed. So control hazard, there is a solution. The logic needed for pipeline to account for branches and also an interrupt, which is delay branch and rearrange the instructions. This delay branch is use of NOP instruction. Solution for branches using delay branch with NOP. When the compiler detects a branch it will automatically insert several NOP so that there is no instruction in the pipeline. So this is your source code, example of your source code. So how many NOP need to be inserted in your table? So this is the number of segment. You need to also minus with 1. K minus 1 is equal 3. You need to pick this value, which is add 3 knob to your source code. Illustrate the space-time diagram. So this one you need to draw by yourself, but you need to see where you need to put the NOP. Later on, if let's say you did not understand, we can also discuss it in our class. Try to do example 18 and I will show you the answer. Please screenshot and maybe you can try to do by yourself. And similar to your example number 15. So we're going to discuss all the example in class later on. If you ask me, you can also ask personally. So there is also another solution. You can see a solution for bunches using rearrange instruction. Total number to move up the instruction, you not going to be set until you confirm that it's going to be error for that belonging task. Then you're going to move up, clear, and so on. So what is the summaries after you have been through all? Instruction pipeline is powerful technique for enhancing performance but require careful design to achieve optimum result with reasonable complexity. Discuss the principles behind instruction pipeline and how it works in practice. And lastly, compare the constructed the various form of pipeline hazard, which is resource, conflict, data dependency, and control or branch difficulty. So that is about your 5.4. We did cover it, and our video this one is part 4.4 part B. So thank you for your watching. Later on we're going to continue with 5.5 and 5.6. Please be safe and bye bye.